Question 4 is the second part of analytical geometry. It specifically looks at circle geometry. In the diagram, the equation of a circle with center M is given to be that. So if we look at our diagram here, the circle that has a center M is a big circle here. And we are given that equation for that circle. They further say here, a small circle with center N touches the bigger circle with center M at the origin and passes through point M. So we are having a small circle here that has a center N. And they say that it touches this bigger circle at the origin, here at the origin. And it also passes through M there. Very critical for one to observe that the bigger circle has the radius, which is going to be the diameter of the small circle. The question continues to say, line RS cuts the bigger circle at E and T, where D is less than 0, C is greater than 0, P is greater than 0, and Q is greater than 0. So now here we have line RS, which cuts the bigger circle at the points E and T, and they're given by C, D, and T, and PQ. And we are told that here the D is negative. Remember, D is a Y value, so it's a value that we're going to read here is a negative number. And the C here is a point on the x-axis and is positive. And the same can be said for the P, which is going to be a positive here, is a point there. It also touches the circle there. And we also have a Q, which is a Y value. That will be positive as well there. The last statement says to us that AB is a tangent to the bigger circle at T. Then we have AB here, which is a tangent at the point T. It touches the circle only at one point there. I think this is a straightforward instruction. Let's see what we can do in terms of answering our questions. The first question says to us here, determine the coordinates of M, which is the center of the bigger circle. So we're looking for the coordinate of this point. Now, we are provided here with an equation that defines the bigger circle. So we can find that center from that equation. However, you have to notice the form in which this equation is written. We have to really convert here that form to a form that says A minus X squared plus A plus B here plus B minus Y squared is equals to R squared. This is our standard form of a circle. Because when we have this form, we are able to simply read X and Y, which are our center for the circle. Now, our equation that we are given is such that we have X squared minus Y squared minus 8X minus 6Y is equals to 0. Now, for me to take this equation to come here, I need to use a method of completing the square. Then I'll be able to change this form to that form. Now, how do we do that? Well, the first step is I'll group the terms that have X together and the terms that have Y together. I'll have here the X squared minus 8X minus Y squared minus 6Y is equals to 0. Okay, notice that here I made a mistake. My Y should be positive. When we are here, we're going to complete the square twice for this part and this part individually. Now, to complete the square, the process that we take for completing the square is that we look at the coefficient of X, which is the 8 here. We take half of that. So I'm going to say half of negative 8 is going to give me negative 4. Then I square the negative 4, which gives me a 16. Now this value of 16 that I got, I'm going to then add the 16 here. But notice something. If you are dealing with equations, what you do on the left, you should also do on the right. It means this side here, I'll have the 0 plus the 16. Because if I don't do this, the equations won't be balanced. And again, what I've done here is a technique where I've done something but nothing. Because if I take this 16 to this side, I'm going to have negative 16, and then combining these two, they give me 0. I really didn't change this equation, it's still the same. Now we are going to do the same for the part that has y. I'm going to take half of negative 6. Remember, negative 6 is a coefficient of y, and half of that will really give me negative 3. Then we square that negative 3. Squaring the negative 3 will give us a 9. That means I'm going to then have y squared minus 6, and we're adding a 9 this side. Because I've added a 9 here, I also have to add a 9 on the other side so that my equations are balanced. Now what I've done now is that I've created perfect squares. This is a perfect square, and also this is a perfect square. So there is a y here. What I mean by that is that I can simply write this as squares. I'm going to have a negative 4 here squared plus, we're going to have y negative 3 squared is equals to, and when I combine the 16 and the 9, they really give me a 25. If you expand this, it will go back to this here. It's a perfect square. I'm squaring the same number twice. And you know, just to give a tip as well, this is the number that we halved that I put here. You can see that my equation now has this form, and it's simply, I can then now read off my coordinates of m. So I'll then say, therefore m will have to be given by a 4 and a 3. This question will carry 3 marks. We'll have a mark for completing the square, for finding our equation, and also writing the final answer. The next question says to us, show that the coordinates of n are 2 and 1.5. So we want to show that these coordinates here are given by that. Now remember, I said the diameter of the small circle is actually the radius of the big circle. This means that this point here is the midpoint of the smaller circle. If I take that diameter and divide it by half, I'll get that. So it means one can find the midpoints using the points O and M. Or already we have this point of M here. So this means if I do half of this point, I should get that point. So in other words, what I'm going to do here is that we are going to say that to find n, we are really going to take a half of each point that we got in the previous question here. I'm taking half of this and half of that, because the diameter of the small circle is the radius of the big circle, and this actually will then give me 4 over 2. Wait, no. This will give me a 2 and 3 over 2. Please try it using the midpoint formula and see what you get. So there isn't much that we're doing here. This question is really just 1 mark for writing that answer there. Then we go to 4.3, which then says to us that prove that the circle with center N, this circle here with center N, and the bigger circle touch internally. So we are requested here to prove that these two circles, they touch internally. In other words, they touch at this point there, just like that. Now, there are various ways of doing this. One of the ways is to notice that these two circles, where they touch each other, they have a common point. That means you can take the equation of a small circle and the equation of a big circle and solve them simultaneously. Your answer, you should get two equal roots. You should get two answers that are the same. And in this case, they're going to be 0, 0 when you solve those two equations simultaneously. And then from there, you can conclude that those two circles touch internally. But I mean, you can imagine taking this equation here and the equation of a small circle, which we can do because of the center. It's going to be really a long simultaneous because, you know, these things have squares here. And, you know, it's going to take time to get to the answer. So I'm not going to use that method, but I'll reserve it for you for practice purposes. What we need to do here, or the easier method that we can use, is to actually compare the radii of these two circles. So in other words, if we are able to prove here that the distance between the centers of the two circles, in other words, this distance here, if we can prove that this distance here, mn, if we can prove that mn is the same as the difference between the radius of the big circle and the small circle, meaning r of a big circle and r of a small circle. What am I saying? Let us look at this on the diagram. If we are able to prove that this distance here, mn, is actually the same as taking the distance from, let me use a different pen so that I make my point properly. If we take the radius here of the big circle, which is the diameter of the small circle, so the big R here, and from that radius we subtract the radius of the small circle. So in this big length here, we subtract this length. What we're going to be left with is this length here. Do you see that? And we're saying that the difference of these two, this length that we get when we subtract them, you can see already on the picture is the same as mn. If that's the case, if we are able to prove this, therefore those two circles must touch internally. Now, from this, then you can see that what we're going to do then is that we need to find the distance of mn using the distance formula, compute the radius of the big circle, and then compute the radius of the small circle and compare those answers. Now, I will start here by saying that mn is going to be defined by x2 minus x1 squared plus y2 minus y1 squared. Remember, I'm using the points M, which are defined by 4 and a 3, and I'm also using the points N, which are defined by 2, 3 over 2. So this means here we are going to have two minus a 4 squared plus 3 over 2 minus a 3 squared. And if we punch this whole thing in our calculator, we should be able to get an answer of 5 over 2. Remember, what we've just calculated is the distance nm, is the distance between the centers of the two circles. Now, what we're going to do then is to find the radius of the big circle. And to find r, which is the radius of the big circle, I can actually use the equation of the big circle that we have here. Remember, we know that this point here is equals to r squared. So that means for me to find r, I have to take the root of this 25. So that means here I'm going to say root of 25, which really is a 5. Now we have found the radius of the big circle. We then are going to look for the radius of the small circle. The radius of the small circle really is half of the radius of the big circle. So that means here I'm going to have 1 over 2 times a 5. Remember, if I take half of this, I should get the r there. Alternatively, you can use the distance formula if you like to find O n. You know, you have the point 0, 0, and we have the point here 2 and 3 over 2. You can compute that. Now, when we do this, we're going to get a 5 over 2. Now, what I'm going to then do now is that I'm going to say r minus r, the radius of the big circle minus the radius of the small circle. And we know that here we have a 5 minus the small circle is a 5 over 2. And if you do this fraction, is a really simple fraction, it's going to give you the 5 over 2, because really 5 over 2 is half of 5. So if I take away from a 5, half of 5, I should get half of 5. Now, at this stage, you then have to notice the relationship that we're talking about here. Our mn is given by 5 over 2, and our r minus r is also given by 5 over 2. So these two are equal. So we have met this condition. It means these two circles must touch internally. So it means now, to answer this question, we are going to conclude to say, therefore, since mn is equals to r minus r, therefore, both circles must touch internally. Must touch internally. Now, this is quite involved really, and you can see that it was out of 5 marks. So where will the 5 marks really come from? The first mark will be given for finding the distance mn. The second mark will come from finding the radius of the big circle and finding the radius of the small circle. Whatever method you use, they'll give you marks. And the other mark really will come from computing this difference between the big circle and the small circle. And the last mark will be you answering the question, analyzing the two answers to say that since mn and r minus r are equal, therefore those two circles must touch internally. Very interesting question. The next question here, which is 4.4, says to us that if the equation SR is given by that equation, so we are looking at SR, calculate the point T. So SR is our line here, which is a secant really, because it has 2 points on the bigger circle. It cuts 2 points on the bigger circle. They've given us the equation of this line here, and we can see that that's a proper equation. Our gradient is 2 there, it's going uphill. So we want to find this coordinate there. I said also in the previous question where we did the first part of analytical geometry that always when I do analytical geometry, I think a lot about functions because we use the same techniques. If you look at this line and the circle, they touch each other at E and T. It means they have the same values. Both the circle and the line have the same values of x and y. And also here, they have the same values of x and y. So that means the two equations must be equal. I must equate the x values and the y values of those equations. I must get the same numbers. So it means I'm going to solve the equation of the bigger circle and the equation of the straight line simultaneously. And we have done this a lot when we did functions. Now, to set up my equations, I'll take the equation of a straight line and say y is equals to 2x minus 15 and call this equation 1. And take the equation of the circle, which I was given to be x squared y squared plus y squared minus 8x minus 6y is equals to 0 to be the second equation. Now what I'm going to do then, I'm going to say substitute equation 1 into equation 2, so that now I'm going to have x squared plus 2x minus 15, x squared minus 8x minus 6, 2x minus a 15 is equals to 0. And from here, this question becomes very, very, very boring, because it's just a simplification process now. We have here the x squared. I'm going to expand the 2x minus 15, and it will give me 4x squared. And in the middle, I'm going to have 2 times 2, which is a 4. 4 times 15, that should give me negative 60x. And if we square the 15, we get 225, and we have here negative 8x. Then we are going to then do the distributive property here, where we're going to have negative 6. No, this is not negative 6. It's actually going to be a negative 12x, because the 2 and a 6 gives me 12. And a 6 times a 15 is going to be a positive 90. And this is equals to 0. Then here I group the like terms. I'm going to focus on my x squared and x squared. I can see that here I'm going to have a 5x squared. Then I'm going to focus on the x and its coefficient, which basically I'm saying negative 60, negative 8. That's 68. Then 68 plus 12, it should give me an 80. So that is negative 80x there. And we are now focusing on 225 plus a 90. I see there a 513. Okay, I'm doing it backward now, because I'm doing it off my head. So this is going to be plus 315 is going to be equals to 0. Guys, you can use your calculator. Now from here, I'm going to reduce this equation, because I can see that, 5 is a factor in an 8, and also 5 is a factor in 115. So I'm going to divide each term here by the 5, so that I can be able to find my factors. If we divide here by a 5, we really get the x squared. If we divide here by a 5, we really get negative 16x. Then if we divide 315 by a 5, that should give me a 63. And remember, what we do on the left, we do on the right. If we divide this by a 5, we really get a 0. Now, when I have something like this, it's easy for me to factorize. I'm going to then break this into 2 products, 2 brackets there, because I'm multiplying 2 numbers. I know that the factors of 63 is a 7 and 9. If I say 7 times 9, I get 63. And I need to then combine these two, either by adding or subtracting, so that I get the negative 16. And actually I can see that if I say negative 7, negative 9, it gives me negative 14. No, negative 16 I meant to say here. So I get a negative 16, 7 and a 9. So it means when I multiply them here, both of them must be negative, and I get a positive. So this is the positive, and this is where I combine them, they give me that. So it means my factors here are going to be a negative 7 and a negative 9. And therefore, we will conclude that our x should be a 7, or it should be a 9. Remember, we are looking for point T. And if you look at our values, 9 should be somewhere here, because it's bigger than 7. So it means here it's a 7. So here it means we need to get a 9. Because 90 is at the far point. So, the bigger number should be that of point T. So that means now, for me to find the coordinates, I then need to take one of the equations here, either this or that, and put the 9 in terms of x to find the y. And you can see that I'm not going to use this equation because it's long. It's already, we have done a lot here. it's easier to then use this equation to find the value of y. But you can try it for practice purposes and see if you really get the same number. So I'm going to say here, substitute x is equals to 9 into equation 1. So that now I have y is equals to the 2 times a 9 minus a 15. That should be a 3. And therefore, this means my coordinates of t are really 9 and a 3. And this was quite a lengthy one. It is going to take, again, a lot of marks, 5 marks here. Let's see where the 5 marks will come from. Well, the first mark will come from equating the two equations. Remember, when I substitute here, I'm saying these equations are the same. They share the same x and y values. So we replace the y value by the equation of a straight line. Then the other part that will give us a mark is really writing the standard form of a quadratic equation, factorizing that standard form. And the other mark will come from finding the x and the y values. And that's how you'll get all the 5 marks. Now the next question here says that write down the equation of a tangent to the circle at point T. And this question really is only for 1 mark. But we have to look at this equation here. This straight line here. If you look at this straight line, it is actually parallel to the y-axis. So that means it's a vertical line. And this will be a line that should be defined by x is equals to. Then the issue now would be how do we determine that x? Because it cuts the x-axis. So we just have to write the number that it cuts the x-axis at. And we can see from this point that it will cut that 9 here, because we said now here that p is 9 anyway. We actually found the coordinates of t to be 9 there. So it means this equation would simply be x is equals to 9. And that is just how you get your full 1 mark there. The next question says to us that OMTQ is a rhombus where Q is the vertex of OQ and TQ. So our point of Q could really be anywhere. For example, I can have OMTQ like that. So it means the Q is here. But if you look at this shape, it is not a rhombus. So it means Q cannot really be there. We can have a situation where it goes to the second quadrant again. You can see that that shape is not a rhombus. Another possibility would be that it could be somewhere here. Maybe this could be a rhombus. Another situation could be that it is somewhere here. Also, maybe this could be a rhombus. And the other possibility is that it would come to this side. And some of these things, if you look at coming to this side, it can't be a rhombus, because you have to remember the properties of a rhombus. A rhombus is a parallelogram really that has a pair of adjacent sides that are equal. So for example, if you look at this pair should be equal, and we know that this is the radius, we need to get another pair this side so that they are equal like that. Now if you move maybe to this part here, maybe we can have this and this to be equal. That could be the case. But if you stretch this to this quadrant, there's no way that these two will be equal, and there's no way that these two also will be equal. So it cannot be in this quadrant. It means now it can be in this quadrant or that quadrant. So for purposes of drawing this, I will really then try maybe to put it so that it is somewhere here. I'll say this is my Q. Now, as I said, this side and this side has to be equal, and this side and this side has to be equal. It's a pair of adjacent sides that are equal for this to be a rhombus. So now in this question, they say that OQ, if we go to OQ and also we go to TQ, OQ, TQ, they form a vertex, meaning they form a corner here. That's where the line would meet. Now, 4.6.1 says calculate the coordinates of Q. We are required to find the coordinates of Q. Now, we know that a rhombus has diagonals that bisects. What do I mean by that? Well, I mean that if I draw lines here in the middle, this line must be equal to that line. Half of this line here must be equal to that line. And also, this line must be equal to that line, meaning half of this line here should be equal to that line. So it means these two diagonals, this line and this line, they cut each other at this point so that they are equal, those sides. That's why we say the diagonals bisect. That knowledge is very important to solving this answer, because what we are going to do is that we are going to find the midpoint of OT. We're going to find the midpoint of OT, meaning this point here, so that we can use that midpoint, because it is the same midpoint for MQ, to find now the coordinates of that. How do I mean? So we are going to do 6.1, where we're going to say the midpoint of OT is really going to be equal to x1 plus x2, y2 minus y1 plus y2, sorry. And this now means I'm going to substitute the coordinates of these 2 points here. Remember, this is 0, 0. Here I'm having the 9 and the 3 is this one here. So it means when I substitute here, I'm going to have the 0 plus the 9, 0 here, and the 9 here. And we are going to divide this by a 2. And here again, we have a 0 for the y value, and it goes with a 3. So it's a 0 plus the 3. And this will give us a midpoint of 9 over 2 and 3 over 2. So we are saying the point here is the 9 over 2 and the 3 over 2 is the midpoint. Now, this same point is the midpoint of this line here, MQ. So that means now I'm going to say that if I have the point of M, the coordinate of M, to be given by the 4 and the 3. Remember, we said this point M here, which is the center of the circle, to be we found it to be 4 and a 3. And now I'm saying that I'm going to use this and the point Q. So the point Q will be defined by XQ and YQ. So this is the point here, Q. Now, if I take the midpoints of these 2 points, I should get that value there. So that means now if I, on the formula of the midpoint, this part here, the X part should be equal to this one for these points. And also the X part here should be equals to this number for these points. Now, so to do that, I'm going to then say here that if I take XQ, I add the 4, remember I'm using this and that over 2. This should be the same as the 9 over 3. Well, it's a 9 over 2 then. And if we solve this, we can see that we're going to have XQ plus 4. I'm cross multiplying here by a 2, so that I'm going to have a 9 because the 22 would cancel, and therefore our XQ is going to be equal to 9 minus a 4, which is a 5. And we're going to do the same for the Y values. I'm going to have for YQ plus the 3. So it is this YQ and the 3 over 2, because I'm taking them from the midpoint formula, remember. And this should give me the same value that we got for the midpoint of the line OT, because they share the same midpoint here. So this means I'm going to have here the 3 over 2. And when we solve this, you can see that we're going to have a YQ plus a 3 is equals to a 3, because again I'm cross multiplying, the 2 and the 2 would cancel, and therefore my YQ would be equal to a 0, because when the 3 comes to this side, it's going to be a 3 minus 3, and that gives me a 0. Then as a result, these are our points. We can then conclude to say, therefore, the point Q would be given by a 5 and a 0. There are other ways in which one can do this, and I think you can explore those ways, because we still have other properties of a rhombus. The last question then says to us that the line TQ is translated so that TQ becomes a tangent to the circle with center O. So what are we doing here? We are moving the line TQ, which is this one. We are translating it. We are moving it so that it becomes a tangent to this circle. So we can move it here, for instance. We can even move it to this side. We can move it to this side. We can move it really anywhere, as long as it becomes a tangent, because we're not told how it's been moved. And then they then say here, point T is also shifted, is also translated, it's moved, such that TM is also a tangent to a smaller circle. So we also move here this point. So we move this point. So it's either I take this point here upwards, or I take it downwards. So if let's say I take it downwards, the line will then be like that. If I take it upwards, the line would be like that. But you can see that if I take it upwards here, it becomes a secant. It doesn't become a tangent. So it means it has to go downwards. It is allowed to go downwards. And that automatically tells me that this line also, we have to move it such that it's sitting like that. It shouldn't be maybe going to that side, because if it goes to that side, it will cause problems. Now, the statement continues to say, and P is a new common point. So this T, when we move it, it becomes a new point P. So at some point here, we have a point P. Maybe let's say it's somewhere here. And my lines are now sitting in a way that I'm going to have point T being moved there, and this one being moved also there. And both these lines are tangents to that circle. The question then further goes to say, give a reason why TQ is equals to TM. Well, I think here I made a mistake of using the same letter. It should be here PQ is equals to PM. Please rectify that, because the new point now is P. So it means now we're saying, why is this line and this line equal in length? What is the reason for that? Well, we know this from Euclidean geometry, that these lines, they come from a common point, and therefore they must be of the same length. It's a theorem. So here we're doing 4.6.3. We will say that the tan from same point, tangents from a common point or the same point, these are tangents that are drawn from a common point.